I'm going to look at the whole regression chapter today. I know that at school you've had a look at it briefly, but I think some of you wanted more work with the teacher input. So we're starting with exponential models. Now, we've actually done this before. We've done it in logs of linear data, where we translate an exponential graph into a logarithmic graph, which then becomes a straight line. And being able to look at linear relationships between two variables is really important, and effectively that is what regression is. So that's what we're doing for all of this chapter, really. To start with, just a quick refresher of the two types of exponential models we may have and how they translate into linear data. So I want to log both sides. Now my left-hand side stayed the same. Here I can use my multiplication rules to split this up. So it becomes log A plus. Now it would be log B to the power of x, but the x comes down in front. So it becomes log xb. So my axes for a graph like this are log y and x. So it's always log y, whatever variables on this side, and it's always the variable on this side. Remember, a and b are constants. So we'd then have our linear graph. Log a is our y-intercept, and then log b is our gradient. In this side, we've got y equals ax to the power of b. We do the same. We're going to log both sides. And then I'm going to split these up. Log y equals log a plus b log x. Could be log x to the power of b. The b comes down. So my axes always have the part with the variables in. So log y, and this time it's log x. It's be a straight line. Don't know why it's particularly steeper. Log a is our y-intercept, and this time our gradient is b. And actually this is quite relevant to us currently. So we've been looking at, obviously in the news has been nothing pretty much except for the coronavirus, and a lot of what they've been reporting, particularly initially, were log graphs. So if you looked at the sort of scale on a log graph, this may be the number of days, and this may be the number of reported cases, and they've done it linearly. So you're going to have 0 to start with. Don't write that as a log. And then you have equal intervals that are done in terms of log or ln, for example. So you might have log 10 of 10. Or what they're going to do is they're going to have log scales that are going up in intervals. And it might be because in a log scale, if I've got log 10 squared, log 10 cubed, log 10 to the power of 4, obviously I've drawn them quite small so they're difficult to see. From a scale point of view, that is 1, 2, 3, 4. From an actual numbers point of view, that is 10, 100, 1,000, 10,000. So imagine this is just individual days. In a real short space of time, that's increased from somewhere between 10 and 100 to 1,000 to 10,000 in quite a short space of time. Now, obviously, this is not real data. Please do not think this is me making it up. But by looking at a straight graph, it looks like things are increasing quite steadily. Whereas if you actually looked at the reality of that graph, it would be showing the increase like this. That scares people. This, because it fools people, it misleads people, they don't think the situation is quite as bad. Now, in a lot of the briefings, they're not using log data, they are actually using real numbers, but some of the data that the government were putting out to start with was using a log scale, which was misleading as to the reality of what was happening. Just interesting, because obviously this is something we are going through at the moment. So go straight on to an example for exponential models. So example 1, they'll quite often here use the large data set to do some bits of information, because it's just a nice way of using the large data set. So the table shows some data collected on the temperature in degrees C of a colony of bacteria and its growth rate. So you've got the table on your screen, because actually we don't need it right now. For an example later, I might copy it down. The data are coded using the changes of the variable x equals t and y equals log g. The regression line of y on x is found to be y equals negative 0.2215 plus 0.0972x. So x means t and y means log g. Mika says the constant negative 0.2215 in the regression line means the colony is shrinking when the temperature is 0. Explain why Mika is wrong. So we have to actually show what the growth rate is. And the only way we can really show what the growth rate is by translating it back into our exponential model. Now, our growth rate is g. So first of all, I know that when x equals 0, I know that t equals 0. So therefore, when y is 0.2215, because when x is 0 and t is 0, that would be eliminated, I know that log g must be equal to that. Now, the growth rate itself is g. So I'm going to rewrite this as a power rather than a log. So log of g is log g base 10. So 10 to the power of this is equal to g. Put that into my calculator and I get 0.60048, blah, blah, blah. So this is positive. So therefore, growth rate is positive and is increasing. Okay, part B. Given that the data can be modelled by an equation in the form g equals kb to the power of t, where k and b are constants, find value of k and b. So I know it can be written in this form, so I now need to translate this into the form that I have got so that I can compare the values. So log g equals log kb to the power of d. So therefore log g is equal to log k plus t log b. So log k is my y-intercept. So log k must be equal to negative 0.2215. Now we've already really worked this out because we're still using base 10. So therefore k is my value from earlier, 0.6. I'm just going to put 0, 0 to 3 significant figures. My gradient, now I know t is equal to x, so therefore log b is my gradient. So log b is equal to my gradient from the linear equation, which is 0.0792. So b is 10 to the power of 0.0792. So therefore b is 1.20 to 3 significant figures. So actually logs for linear data is fairly straightforward, as long as you can use your log rules to rewrite that in log form. Most of this chapter is not looking at that. It's just a reminder of that kind of linear data, and it'll probably lead into something related to correlation. Now, you've done correlation before at GCSE in a very, very, very vague way, in that you've talked about positive correlation or negative correlation. Now, we look at actually calculating correlation. You will need your calculator for this next part. Now, it's called, the value we get is called the product moment correlation coefficient, or sometimes just called the PMCC. And this is a number that tells us or describes the correlation for a sample of data. And we call this, for a sample of data, R. So I'm going to do sort of my correlation scale. So we've got -1 and +1, and in the middle we have got 0. So anything that is between 0 and -1 is a negative correlation, and anything between 0 and +1 is a positive correlation. In terms of describing it, this is all relatively rough, but this is what I've used to give me an idea when I have done it, when I did the IB. And it's always looking at quarters. This was how we did it then, and I think it'd be very similar there. So if it's between plus or minus 0.25, we'd basically say there's no correlation there. It's so, or it would be described as very, very weak, because it's so small that really there isn't much of a correlation there really at all. So the book says if R is 0 or close to 0, then it's no correlation. I would call that pretty close to 0. If it's between plus or minus 0.25 and 0.5, that's generally a weak correlation. Between plus or minus 0.5, 0.75, we would call that a moderate correlation. So it's moderately negative and moderately positive. And then between plus or minus 0.75 and 1 is a strong correlation. So a strong positive or a strong negative. So we can calculate the PMCC on our calculator for data and use that to describe a correlation. So, example, against data from the large data set. From the large data set, the daily mean wind speed, and actually I think I might have said the first one was from the large data set and it wasn't. I think I just assumed because most of them from this chapter are, so I apologise about that. From the large data set, the daily mean wind speed, W knots, and the daily maximum gust, G knots, were recorded for the first 10 days in September in Herne in 1987. State the meaning of NA in the table above. So actually what I'm going to do so that it's easier for reference for pretty much all of this. Question is draw very quickly the table out. So we've got W knots, which is the wind speed, and G, which is the maximum daily gust. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. You obviously don't need to copy this down because you'll have the PowerPoint in front of you, but because I should have prepared this in advance, yes, but I haven't, sorry. So, here's our table. It says, state the meaning of NA in the above table. Well, it simply means the gust was not available, or the maximum gust was not available on these days. So NA just means it's not available. Trace is the other thing they use on different ones. Make sure you know what that means as well. Calculate the product moment correlation coefficient for the remaining 8 days. Now, they may not say for the remaining 8 days. They may say for this sample. If they do, obviously, please do not use the ones with NA because you don't have data. Do not just assume 0. because that's just not true, and that will massively impact your correlation. So, on your calculator, I'm going to do menu, and you're going to go to number 6, statistics. Now on that screen you have various things. You have one variable, y equals a plus bx, etc. So these are different statistics you can calculate. So they're one variable stats. So when you did year 1 stuff, you should have been able to use that for things like standard deviation and means, etc. We want number 2, which, as you can see, is a linear equation, so that gives us a linear regression. So I'm going to press number 2. Then you get a table. So you get x, you get y, and you get frequency. For this table, you'll only need x and y. The frequency only works if, let's say, you have you might have the number of days that there is a certain amount of rainfall, and let's say the maximum sunshine level on those days, for example. That's not a very good example, but it gives you an idea where you might have actually a frequency table as well as a second variable. We've just got x and y. So x is going to be my w. So I'm just going to type in my values. So I'm only going to do the days that I actually have gust speed for. And I'm going to go back up to the top and type in the gust speed. So when there's a wind speed of 4, there's a gust speed of 13, then 12, 19, 23, and so on. So I'm literally just typing in the values for my table. When I've done this, so I'll write that to the side. So menu, 6, statistics, then you choose 2, y equals a plus b, x, and then you fill in the table. And then you're going to press the option button. And we want, number 4, the regression calculation. So I'm going to press 4. Now it gives you the equation of the regression line, which you may well need to record. So this regression line, A is our y-intercept, our constant, and B is our gradient. So that gives you the regression line. You may need to actually write that down, so it's worth you knowing. And R is our PMCC. So in this case, it is 0.953 to 3 significant figures. Now, quite often, the book reports 4 significant figures. In this case, that's not necessary because we have everything to 1 or 2 significant figures, so 3 is plenty. In cases where you've actually got things reported to 4, then you should do it to 4 significant figures. I don't think I have in some of my examples, but you probably should. So R is 0.953. With reference to your answer to part B, comment on the suitability of linear regression model for this data. So R is close to 1, so it is a strong positive correlation. Now actually, the word positive probably could be eliminated in terms of actually the importance is it's a strong correlation. This means data lies close to a straight line, so linear regression is suitable. So for anything that is a strong or moderate correlation, this probably is suitable. If you were using if you had a weak correlation, then you'd probably say that linear regression model is not suitable. Okay, so on to the final part. This is mostly just practice using a calculator for these first 2 sections. First one looks for linear data, second one actually using your calculator. So we're now going to move on to hypothesis testing, which is always everyone's favourite. I think correlation hypothesis testing is pretty straightforward. So effectively what you're doing is you're using a hypothesis test to determine whether the PMCC, so the R value for some data, indicates whether there likely is going to be a linear relationship. So is there going to be a correlation? So we always, no matter what type of test we do, assume that there is no correlation. So we're always assuming that there is no correlation, and we're testing to see how likely it is that there is correlation. We're actually going to use P in this. So PMCC, P, is the PMCC for the population. R, which is what is calculated, is the PMCC for the sample. This is all we need to worry about actually calculating. P we can find in a table, which I'll show you shortly. So if you have a one-tailed test, oh, that L looks really dodgy, sorry. One-tailed test, then either we are testing that there is a positive correlation, or we are testing that there is a negative correlation. For a two-tailed test, again, we always assume that there's none, but we are just testing that there is a correlation either way. That's all. Okay, so that's the difference. So we do two examples, one looking at each style. Now we are going to do it using this table. Now you have a table similar to this in your textbook, which is on page 191, but it doesn't have the Spearman's one. You do not need to worry about that. Okay, so I think the Spearman's coefficient possibly is from, say, stats, further stats, if you were to do it as an option in further maths, which you guys won't be doing, you'll be doing decision. So you don't have to worry about that. I only look at this side. This is how it will look in your exam booklet, okay? So, sorry, in your formula booklet. So ignore that side. We're only looking at this side. And what this gives us is the critical values. There may be a way to do it on your calculator. I don't know how to do that, okay? So I am showing you how to use the table because actually it's quite straightforward. So this is your sample size. This is the critical value. So let's say we're looking at a sample size 4, and I want to look at the significance at the 5% level. So this is the modulus value. So that would mean if I was testing for a positive correlation, it would have to be bigger than 0.9. If I was testing for a negative correlation, it would have to be smaller than a negative 0.9. So negative 0.95, for example. Basically, it has to be a stronger correlation than any of these values to be the cutoff, okay? But I'll show you what that means when we actually do an example, because I think in this case that is easier. So, example number 1. A scientist takes 30 observations. So I'm just going to put N is 30. The scientist takes 30 observations of the masses of 2 reactants in an experiment. She calculates the PMCC for this sample to be R equals negative 0.45. The scientist believes there is no correlation between the masses of the 2 reactants. Test at the 10% significance level, the scientist claims stating a hypothesis clearly. Okay, so she believes there's no correlation. You need to test that there is. Therefore, this is a two-tailed test. There's nothing that tells you to look positively or negatively. The fact that she got one that's negative still doesn't mean it's a one-tailed test. Her sample could be rubbish. You just want to test whether there's no correlation. I'll show you the language in the next one, which implies that it is one-tailed. So, my null hypothesis is that there is no correlation. My alternative is that there is some kind of correlation, okay? So this is my hypothesis. Because we're at the 10%, obviously that means we're testing at 5% each end. That is why it's really important that we're looking at the two-tailed. So now I'll look at my table. So I've got a sample size of 30. Now you won't be able to see this. And I'm looking at the 0.05 section. Okay, so I'm looking in this column, sample size 30. So the value I get, sample size 30, the critical value is 0.3061. Now I've put the modulus around it, you don't have to. Because it means, I'm just saying it's working both ways. So 0.3061. So therefore, the critical region is that R needs to be bigger than 0.3061 or R is smaller than negative 3061. One of those will tell us that there is a correlation either way. Now we need to compare. So negative 0.45 is less than negative 0.3061. So we need R to be less than it, so it is. So therefore R is in our critical region. So we reject our null hypothesis and accept our alternate hypothesis. So there is sufficient evidence of a correlation between the two reactants. Now, of course, in this case, there is sufficient evidence that it's a negative correlation. We are not going to worry about that because this one, she just wanted to test whether there was a correlation or not, okay? So we don't need to say that it's negative. All we're doing is testing whether there was a correlation. There is evidence that there's a correlation, so don't add negative. I think if you did, you probably wouldn't lose marks, but you just don't need to. Okay, got one more example to do, and I probably can fit it in there. So example number 2, the table from the large data set shows the daily maximum gust X knots and the daily maximum relative humidity Y% in leaving for a sample of 8 days in May 2015. So I'm not going to copy it out this time, but part A says find the PMCC, so finding R. So menu 6 for stats, 2 y equals a plus bx. So I'm just going to type in my data. Oh, I didn't want to do that. 28, 38, 37, 18, 17, 21, 29. Then I'm going to do my y's. 99, 94, 87, 80, 80, 84, 86. Okay. Option regression calculation. So R is equal to 0.1149 to 4SF. Now I've done 4SF because I know that I'm going to be using that table. Okay. So it's going to be 4 significant figures. Now that is quite a weak correlation. You don't need to comment it at all now, but it is a very weak correlation. But depending on what the cutoff is, it may be sufficient. You can probably guess it won't be, but let's see. So, test at the 10% significance level whether there is evidence of a positive correlation between daily maximum gust and daily maximum relative humidity. State your hypotheses clearly. So our null hypothesis is always that there's no correlation. In this case, our alternate is that it's greater than 0. It's a one-tailed test. And our sample size is just the number of days we have, which is 8. So my critical value from my table. So I've got a sample size of 8. I'm testing at the 10% significance level. So it is this value here. Use a ruler in the exam if you're not sure that you're getting the table right. So the critical value is 0.5067. So the critical region is that R has to be greater than 5.67. Only greater this time because we're just testing positive. 0.1149 is less than 0.5067. So therefore, R is not in our critical region. We accept our null hypothesis. There is not sufficient or insufficient evidence that there is a positive correlation. And that is it with these hypothesis tests. They're probably not going to be worth as many marks because of that, but it is just a matter of familiarising yourself with that table. Obviously, any questions, send me an email, send me a message or show my homework, but that is it for regression.